Right now we have Sharon from Lyft presenting machine learning talk. Welcome, Sharon.
Thank you.
And at the end of the talk, I'll be coming around with the mic for any questions.
All right, thanks. So, hello, everyone. Can you all hear me well? Okay. First of all, welcome to Women Who Code. Like, when I entered the building this morning, there was like so much excitement and so many people. I was even happy to see like long lines outside the women's bathroom, which is rare for a technical conference. So my name is Sharon. I'm a software engineer at Lyft, and I work on the streaming platform team at Lyft. And more recently, I have been working on building a machine learning platform to make it easy for our research scientists and data scientists to prototype and run their machine learning models, so generate features for their ML models. So first, I wanted to talk about, before we start, like how do we use machine learning at Lyft? So you all probably already know, but Lyft is a ride-sharing company. Our mission is to improve people's lives through the world's best transportation. And to that end, we want to make sure that everyone has a good experience on the platform. And that means accurate ETAs, fair pricing. We want to notify users if there are delays and things like that. To predict like accurate ETAs and to decide like how to price the ride or like to detect fraud on the platform, we use machine learning models that make these predictions. And as you can imagine, a lot of parameters that go into these decision making change very rapidly. So things like traffic patterns, weather conditions, whether or not there's a game happening at AT&T Park or Oracle Park now, I guess. And if there's an accident somewhere. So these are like parameters that are constantly changing. So we want to use the most recent view of the world in order to make these decisions. Which means that we want to process our data, the events and data that is generated on the platform, in a very low latency, in a very real-time manner. So we have all this data that's produced on the platform. We have an event ingestion pipeline that processes these events, ingests these events, and it's available to the system within few milliseconds of the events occurring. So we have the data. Now, how do we draw insights from it in real time? And we want to do it properly. And we don't want to be this guy. We don't want to just stir the data and hope for good results, right? So we wanted to go into it in a methodical manner. And there were a few requirements that we had when we set out to build this. So the most important thing was we wanted to make a system that was self-service and fully managed. And what that means is that we want to make sure our users, so our users being research scientists, data scientists, machine learning engineers, they are effective in their work, and we want to remove all other distractions. So we don't want them to have to learn a new programming language to onboard onto the system or worry about deployments or resource management, any of that. So we wanted this to be fully managed. We also wanted to build a fault-tolerant system because, well, it's a distributed system. Things happen, things go down, but we wanted this to recover in a graceful manner. And the most important part was the low latency and correctness aspects. So we want to process the data very quickly. We want to build the most latest state of the world as soon as it occurs, and we want correct computations. And for that, we decided to use stream processing. So what exactly is stream processing? So in order to understand that, let's look at sort of like the history of data processing. So first came batch processing. So things like MapReduce, Hive, and Presto. And the way it would work is that it would run we could run MapReduce programs on data sets that were available on HDFS, for example. But the biggest requirement for these was that the data needs to be complete before you start a MapReduce program. You can't stream data into it while the program is running. What that means is that depending on the amount of data or the for the amount of times worth data that you're processing, you have to wait for the data to be complete, which means latency in hours or sometimes days. If there's traffic jam on 101, we want our ETAs to reflect that as soon as possible. So waiting was definitely not an option for us. So then came micro-batching systems. So micro-batching systems such as Apache Spark. Apache Spark is an example. And what they did was, so now micro-batching systems could work on streaming data, on real-time data. So the latency is reduced. So now we don't need the data to be complete before processing can start. And the way it works is, as the data comes in through Kafka or any other Kinesis or any other stream, it's accumulated in small micro batches, then processed, and the results are written to storage. But there was an issue with this. In a distributed system, events can be late, events can come out of order. So what happens in that case, right? So in this case, what happened was this one was a little late. It came right after the first batch where it was supposed to go finish processing. So it went into the wrong batch. So now the result is incorrect. So it was giving us improved latency, but the correctness wasn't there. So we decided to use stream processing. So now stream processing also works on real-time data, but there is no concept of batch. So there is no waiting for a batch to fill up in order to perform any processing. So each event is processed individually as soon as it arrives. So the decisions about which state needs to be updated based on this event, it's all made individually. But you might be wondering, like, if each event is processed individually, how does stateful processing or windowing works? So for that, let's look at an example. Before we go into the example, I want to talk about windowing. So windowing is sort of at the heart of stream processing applications. And the reason is because stream processing works on unbounded or infinite streams of data where data is coming every milliseconds. So we want to divide data into finite sets. And these can be, so this is what windows are. So windows are based on time, and they can be fixed windows. So fixed windows, 1 minute windows that move forward every 1 minute. They can be sliding windows, and they can even be session windows. So session windows based on user session, when the user logs in to a website, does some stuff, closes the session, that's a session window. So now let's look at an example. So who all are excited about Game of Thrones tomorrow? I'm super excited. Yeah, I have last 2 weeks I have done nothing else other than watching YouTube theory videos about who's going to die next and all that stuff. So to measure this excitement from others in real time, what I want to do is I want to count the number of tweets that are sent out while Game of Thrones is streaming on a minute-by-minute basis. So my theory is that people tweet a lot when they are watching TV shows or games, and the volume of tweets will give us a little bit of an idea about what were the more popular scenes, right? So for that, I wrote this Flink streaming SQL program. So what I'm doing here is I'm saying that from all the tweets, I want to filter the ones that have text like Game of Thrones or GOT, and then I want to bucket these in 1 minute buckets based on the tweet time. And I want to report the count. So if you notice something over here, I'm not using the clock time To bucket it, I'm using a parameter on the tweet itself, so the tweet time, to bucket it into 1 minute windows. But so to understand how this works in a real-time system, let's look at the concept of time. So how time works in a stream processing system. So there are basically two main notions of time that are important to stream processing system, and one is processing time and event time. So processing time is the system time when the processor or your program actually sees the event. And event time is the logical time when the event happened. So to give you an example, suppose I saw someone die in Game of Thrones while I'm watching it, right? And I'm about to tweet it. And I wrote my tweet and I hit send, but Twitter went down. So my tweet wasn't sent. So it went down, 5-6 minutes passed, Twitter came back up, and then it started processing all this backlog of tweets. So we see a big spike as soon as Twitter comes back on. But that doesn't work in our use case because we were correlating the volume of tweets to the popular scenes. So processing time doesn't work for us. So that is where event time comes. So event time is like the time when I actually wrote the tweet. In an ideal world, if you draw an axis between processing time and event time, it would look something like that. And most events, like this 3 over here, would be along this axis. But, due to network latencies and all sorts of stuff, events are delayed, and it would be more like this 9 over here. So this 9 was the event time for this 9, or this event occurred sometime right after 12:01, but our system saw it at 12:08. So this is where event times are important. But you might wonder, I did talk about real time and latency, right? So how long do we wait for these events? Events can be late, but we do want correct results, but how long do we wait? And sometimes they can be really late. I mean, Star Wars came out in episodes 4, 5, and 6 came out first in 1977, 80, and 83. Then episodes 1, 2, and 3. And then later, more recently, Rogue One came, which I think is which in my opinion is an extension of episode 3. So it's all complete madness. It's all a complete out of order, arriving really late. So how long do we wait for late events? So this is where a watermark comes in. So a watermark is an estimate that all events with an earlier timestamp have been received. And this is, a watermark is a heuristic that we give to our stream processing system to tell the stream processing system that anything that before this watermark has arrived. So in an ideal world, this would be our watermark, but because of delays and all, this is a more real scenario. So let's look at an example to see how watermarks are used. So this is an example of a batch processing system. So our use case is that we want to count the number of integers, or we want to sum the number of some integers in 2-minute windows. So we have these numbers that are coming with timestamps, and we want to calculate the sum in 2-minute windows. So in a batch world, when we have all the data before the program runs, we start the program, it starts accumulating the sum. When the program ends, it reports the results. It's all great, and we get correct results. But what happens in a real time, in a streaming world where we don't know, we don't have complete data, data is constantly coming. How do we make the decision as to when to close the window? So for this, we added watermarks. So the green line over there is our heuristic watermark. So what we did was, as the numbers are coming in, we calculate the sum. So in the first window over here, the sum is now 5. Then the watermark was encountered. And then the system decided, OK, the watermark is passed. I am not expecting any other events for this window. I'm going to report this window as complete. So that gives us a good latency. So we are getting results in real time. But you might wonder, like, we did have a requirement that we also want correct results. So the 9 over there is left out now. So what happens? So as a developer, you can make the decision. So Flink streaming is a stream processing system that allows you to re-trigger windows when late events come. So your windows will be eventually correct. So it will still be fast, but it will be eventually correct. So these are all the good things with processing. So how did we finally build streaming at Lyft? So we decided to use Apache Flink, which is a stream processing system. And it provides a low latency, high throughput way of processing real-time events. Event time processing is supported, which was super important for us. And fault tolerance is available in the event of failure. And this is enabled through Flink's checkpointing mechanism. So Flink allows you to take snapshots of the program regularly. So if everything goes down and when the program comes up, it just has to restart from the last snapshot. It doesn't have to reprocess the whole thing. So that was great. And it also supports exactly one semantic, so correctness, which was very crucial for us. At Lyft, we currently have about 80 plus Flink jobs in production. Tens of millions of records are processed per second. We currently use our custom deployment method that runs on EC2, and very soon it will be supported on Kubernetes. And Flink SQL, the SQL that I showed you earlier, that is an example of a lot of machine learning feature programs. So it's like few lines of code. Almost everyone is like familiar with SQL. If not, it's easy to onboard to. So it was really good for our machine learning platform use cases. And out of these 80 jobs, about 65 are Flink SQL jobs. And this is the architecture we finally built. So as I mentioned, like apart from the low latency computation, the other thing that was super important to us was self-service and fully managed system. So we wanted to build a system that was really, really easy to use. So for that, what we did was we abstracted away all the things that goes into running a distributed system. So now our user would just give us a configuration file that looks like this. Like who owns this feature, they will give us the SQL query, they'll give us the feature definition, and the sinks. So basically, like, where do I need these feature data to be stored? And that's it. That's like a few lines of configuration file. Then our control plane takes that configuration file, parses it, and then validates it. Given the SQL, it finds out, okay, this is the event that they want to aggregate on. Let me go and find, like, where can I get these events? Like, which Kafka stream has these events, or which S3 partition has these events. So our control plane will do all that, like magic, and pull out all the information it needs. And it will also figure out what the shape of the distributed system needs to be in order to run this program. So, like, how many instances do I need? What are the containers like? What are the Docker images that I want to install? And once it does all that, it generates a job config, which this is obviously not complete, but it's something like this. So it's all the container data, metadata, like a bigger job file. And that is sent to our Flink Kubernetes cluster. And the Flink Kubernetes cluster just looks at this job file and, okay, for this to run this job, this user needs like 5 instances. Let me get those instances. And then I'll install these Docker images, and so on and so forth, and just run it. So all those details are completely abstracted away. And this is what an actual like Flink program, or like an end-to-end program, looks like. So events are produced in our platform, and those events are sort of ingested by our event ingestion system and made available in external storage like S3, and also like Kafka and Kinesis streams. And the Flink program would just read data from these sources, perform all the computation, windowing, stateful processing, write results to a Kafka stream. Then another Flink program would read from this Kafka stream and just fan out the results to all the places that it needed to go to. So we have sort of like separation of concerns over here. So the first one is just interested in performing the business logic, like processing the data. And the second Flink program is responsible for making sure it goes to all the right places. Now, what were some key takeaways? So I already talked about like some of the good things, like fault tolerance and high throughput, low latency. But there are some lessons we learned. One is bootstrapping is hard and also really critical to consider when you're writing a stream processing system. And what exactly is bootstrapping in the context of real-time systems? So suppose I'm writing a feature and I say that, okay, I want to count the number of tweets in a window of 7 days. So if I start the program today and it starts reading data, in order for it to correctly answer this query, it needs to run for at least 7 days. Now, after 7 days, I've spent 7 days, I look at it, and I realize, oh, my logic is wrong. And then I have to redo that whole thing and wait for 7 days. And how about forever? Like, what if I want to count the number of tweets like forever, right? That doesn't scale. So for that, we need bootstrapping. So what bootstrapping does is we look at, in order to build the current state, we look at historic data. So we look behind 7 days. We look behind, build up the state, and then as new data comes in, we keep that state fresh. And that's tricky to do depending on your on the window size. So suppose my window size is like 2 months. So some of your data sources may have a retention of like 3 days. Like for example, Kafka sometimes provides a retention of like I think 7 days, something like that. So you would have to get data from like multiple sources. Which leads me to the next point. So source queue. So when you are reading from multiple data sources, and if there's a skew in time, that can lead to performance degradation. And that's something that my team at Lyft is like working on, and it's already out for proposal. The third thing is stream processing systems have very high throughput. So if they are writing or calling microservices directly, you can easily end up DDoSing a microservice. And we learned it the hard way, to be honest. So special care must be taken when streaming systems have to talk to microservices. So things like rate limiting, throttling, these should be in place. The fourth is missing or wrong watermarks. So as I mentioned earlier, watermarks is the way time moves in a stream processing system. So stream processing system understands time in terms of watermarks. So if it's missing, time stands still and nothing happens. Or if the watermarks are wrong, then the time can be all wonky. So that's an important thing to consider. To sort of close off this session, I've added some further reading material. You can Google these. Otherwise, I think they will be sending out the slides, so there will be an URL. So data flow model is this paper that was co-written at Google. So some of my images that I used in the slides are from there. So Tyler Akidow and Francis Perry from Google, they worked on that. And then, so data flow model explains like in more detail about like processing time, event time, watermarks, and all the intricate things about stream processing. Then bootstrapping state in Apache Flink is a talk that one of my teammates gave, and it talks about more about challenges of bootstrapping and how to do it. And we have this Jira ticket, which also has the design document for how we are solving the source synchronization problem. So that was all I had. And before we go into questions, shameless plug, we are hiring. So, hit me up if you want to know more about Lyft or the streaming platform or machine learning team, anything. And I don't know how much time we have, but if we can't get through all the questions, I'm happy to answer questions outside in the halls if you meet me.
So I'll go around with the mic. Anyone have questions? Or who's first? Okay, if you're all shy, maybe you can come separately after the talk. Oh, we have a question.
Hi, I have a question on, can you give us an example on how this is being used at Lyft? Because all the examples you've given are not like Lyft direct related, so I'm super curious.
Yeah. So I can talk about, so let's see. So for example, there are some, so I talked about like fraud being like one of the important things that we want to combat. So in one use case, we wanted to see like we wanted to behavior fingerprint to see like what kind of actions people are taking. So suppose someone is like rapidly entering like multiple different credit cards one by one, that's definitely an anomalous situation, right? So and fraud models change very quickly, and we want to like find these in real time. So for that, what we did was we looked at like these kind of situations where, you know, we would look at events like payments events or something, payments events for the last 60 days, and we would like count the number of times they attempted to enter a new credit card. So that's an example of fraud. Then we also have like things like we want to see like if people are canceling their rides in a geo hash, for example, so which gives us an idea of maybe there's something going wrong over there. Maybe the ETA is wrong, or maybe like something that is causing so many higher amount of cancels than normal. So yeah, so things like that. Hey,
Oh, hold on.
Can you tell me how did you decided to choose Apache Flink?
Yeah, so when we were thinking about this, like so Spark was something that some of our teammates were familiar with, but as I mentioned, there were like for some cases it wouldn't work for us. And Apache Flink was at that time, like when we started using it almost a year ago, when we started building it almost a year ago, Apache Flink was almost at, I think, version 1.4, 1.5, and it had like Flink SQL support, and SQL support was super important for us. So the rest of Lyft uses writes code in Python, and a lot of streaming or processing systems require jobs to be written in Java and so on. And that's like that adds like time to onboard new users. So Flink SQL was one of the reasons. And in general, like Flink is amazing in the sense that with all the checkpointing support that it has, and it worked really well for us. And when we started using it, even before that, there were stories from like Alibaba, and I think Netflix had already been using it, so we already knew some success stories. So yeah.
Did you find that stream processing was more expensive or less expensive? And obviously it was more beneficial. Was it worth the cost increase if there was any?
Right. So I'd like to add that stream processing may not be the best situation for everything. So with stream processing, there's you have to manage state. Like you have to manage state in real time, and then so for that we need like extra resources and all of that. So suppose if your use case, if latency is not like a big requirement for you, and you then I would recommend like batch instead of streaming, because with streaming, so I can tell you like one interesting use case. So so for bootstrapping, what we did was so we had these two different sources we were reading data from, and during the bootstrap state, because we are building state by looking behind, we need extra resources at that time. So we would run this program with like a very high parallelism, and once it finishes bootstrapping, we'd kill that program and then restart it with a smaller parallelism, because Flink has this weird thing where if you want to apply a snapshot from one program to another, the shape of the program should not change. So So we had to like sort of have this manual process to do that. If there was a way we could like promote snapshot from a like a batch processing program to a streaming program, that would have been better. So yeah, I would say if your requirements are like low latency computations, and if state management and everything is really important to you, then streaming works. If latency is not that big of a requirement, then maybe batch processing works better. Yeah.
I think we'll have one last question, so let's take everything else like offline after that. Thanks. I had one question here. Sorry. Okay.
Hey, hello, how are you doing?
Good, how are you?
I wanted to ask you about models.
About models?
Yeah.
Yeah.
I was wondering, you say that an example that you're doing is fraud detection.
Yeah.
So I was wondering, have you guys come up with your own model, or you're just using the normal models?
Yeah, I don't know about that because I am not in the machine learning team. I'm just building a platform for them.
Oh, okay.
Yeah, so I'm sorry.
It's okay.
Yeah.
It's okay. I just wanted to know.
Yeah.
Awesome. Thank you, Sharon. Thank you so much.